Any questions? No. Okay. So today our main aim will be to discuss the physics behind the black hole horizon. Okay, we'll see what the concept, how the concept of horizon arises. But I thought before I do that, okay, I'll discuss briefly this phenomenon of turning around the rho versus phi graph, because I think some of you had expressed confusion. So let me discuss that first. So turn around of rho phi graph, right? Basically the fact that d rho d phi changes sign. That's what we want to see. And the essential point is the following, that we are trying to solve an equation like this: d rho d phi equal to some function which I can write as 1 over square root of 0. Okay, I will not write down specifically what 0 is. Okay, you can work out from the expressions that we had. The only thing we need to know for this purpose is that 0, if you plot g versus rho, then there are two values of rho minus and rho plus, such that 0 is positive in this range and it's negative outside. Okay, I drew the curve in the x space yesterday, but it's the same in the rho space, that 0 is positive in some region between rho plus and rho minus and rho plus, and negative elsewhere. Okay, and just this will be enough to understand what happens when you reach near rho plus or rho minus. So the idea is that we study the differential equation near one of these. Okay, so let's say near rho equal to rho minus. So somewhere here. In this case, we can expand 0 in a Taylor series expansion around rho minus, because we are close to rho minus, and the Taylor series expansion will take the form of c times rho minus, with c being positive. Okay, some constant c plus higher order terms. C is positive because the slope here is clearly positive, right? Because for rho larger than rho minus, this function is positive. For rho less than rho minus, this function is negative.
So 0 equals to 0, that the 0 d phi will diverge. Write it as 1 by root over 0.
Yes, d rho d phi will diverge, but that's okay. No, this is, let me just check the, sorry, this is d phi 0.
Yeah.
This is d phi 0. Okay, so now what we'll do is that we just solve this equation near this range, okay, using this formula. So we get d phi d rho is 1 over square root of c times rho minus rho minus, and this tells us that phi is phi naught, this is the integration constant, plus 1 over root c half rho minus for half. Okay, plus higher order terms which you don't care right now, because you are studying the system near rho equal to rho minus. So we can rewrite this as rho minus by just by squaring it, equal to 4c times phi minus square. Okay, what this means is that as phi passes through phi naught, suppose this is rho versus phi, this is our rho minus, this is phi naught, this is phi naught is the place where rho reaches rho minus, because this is 0. But this says c is positive constant, so basically rho behaves like this, right? So d rho, the rho versus phi graph turns around precisely at phi naught. Okay, when rho becomes equal to rho minus. Okay, so this is a consequence of the differential equation. Physically, we know that it had to happen because 0 couldn't be negative, right? Then the equation doesn't make sense. And the equations themselves tell us that yes, that's what happens. That rho versus phi will turn around. Okay, so the rho never goes below rho minus. Is this clear? Pardon? So there will be something wrong. I took phi minus phi naught and then I squared this, right? So 4c times phi minus phi naught whole square is equal to rho minus rho minus. Pardon? Integration. Yeah, I already did the integral. I solved this equation, right? So this is the integration constant. Oh, this is 2, okay. Sorry. That's not 2. This is 2. So the 2 will come, this 4 will come. Is it okay? Now we can do the same thing near rho plus. So near rho equal to rho plus, what will you get? We will get 0 equal to some other constant d times rho plus minus rho with d positive. Because for rho less than rho plus, the function is positive. For rho larger than rho plus, the function will be negative, right? That's what is reflected in this. So again, substitute in the equation, d phi d rho is 1 over square root of d times rho plus minus rho. So we can solve, we can integrate by as phi equal to some other constant, say phi tilde naught minus 2 over root d times rho plus minus rho. This minus sign or plus sign actually isn't too important because there is a square root anyway, right? And we don't know which sign of square root to take. Okay, but we have just taken some sign. So this tells us that rho plus minus rho is d over 4 phi minus phi tilde naught square. So rho is rho plus minus this, which means rho actually reaches rho plus and then turns around. So if this is our rho plus, it will turn around like this. Okay, so this is our phi tilde naught.
So sir,
Yes.
sir, in previous class you told that there were plus minus sign in your equation. These things are
Plus minus, yeah. This, I mean, when I wrote this could have been plus or minus. Okay, but in getting to this form, it made no difference, right? Because I could have taken put a plus minus sign here, this would have been a plus minus sign. But I am squaring it, so this form will still be true.
So actually in the whole motion only one differential equation is followed, not plus minus, right? They would
Well,
change
it depends on whether if this square root is always a positive square root, then it is plus and minus, right? Because there are regions where d phi d rho is positive, there are other regions where d phi d rho is negative. Right? So it depends on how you interpret the square root. Right? If you interpret the square root either as a positive square root, then you have to put plus or minus. Because every time the thing turns around, you can see from this diagram, right? The d phi d rho changes sign.
The idea is that if I go just beyond phi to phi, just beyond phi naught and just behind phi naught, then the
Signs are different,
signs
yeah.
are different.
So it changes its actual equation to another one. Like if I write something like root of this thing, then it will go to a minus of.
Yes, if you interpret this root as positive root, right, then it will go to negative of itself. Yes.
But if you are getting this result by not substituting plus or minus.
No, I could have put a plus minus here. Plus minus here, right? But when you take phi minus phi naught and square it, It's the same equation. Right? So the plus minus sign here doesn't really make a difference. Similarly, I could have put a plus minus sign here. This should have been minus plus, but this will still be.
Sir, your delta pi is phi tilde naught minus phi naught by that twice of this.
Delta phi.
That you calculated yesterday.
Yes, yes. Delta phi will be phi tilde naught minus phi naught times 2. Yes. Right? So basically you don't need to integrate it from here to here.
From this part itself, it will tell me whether 0 d phi is negative or positive. If d is greater than 0, this is a greater quantity. So 0 d phi should be.
No, because when you take the rho plus minus rho, you have to take the square root, and square root can be plus or minus. See, 0 d phi is sensitive to the square root, right? So the rho plus minus rho is always this, okay? But 0 d phi, I mean, when you try to calculate, it becomes a square root, okay? And there you can have plus or minus sign.
That overall sign probably has the sense of clockwise or anti-clockwise rotation, like how you are perceiving the rotation of the body, the revolution around the center.
Which one?
This overall sign in d phi by d rho.
No.
Yes.
Like you perceive the rotation as making the positive sense or in the negative.
No. Rotation d phi dt is always positive. We have taken because that cannot change, right? Because d phi dt is k times rho square, and I have taken k to be positive. So as a function of time, phi is always increasing. Okay? But rho is going up and down. Okay? See, if you express it in terms of phi, right? It depends on here whether d rho d phi. Suppose you are trying to calculate d rho d phi. Okay? You can, if you think in terms of phi, it looks like that there is no sign, there is no plus minus. But phi can be less than phi tilde naught to larger than phi tilde naught, right? So as phi passes from less than phi tilde naught to larger than phi tilde naught, this one will change sign, d rho d phi will change sign. If on the other hand you write express in terms of rho itself, right, by using this equation, then there will be a plus minus sign. Because when you convert phi minus phi tilde naught in terms of rho, okay, it's plus minus square root of rho plus minus rho. Okay. So if you think of this rho as a function of phi, there is no confusion. Okay. But that doesn't mean that the sign doesn't change, right? Because phi minus phi naught can have both signs.
Sir, last day in case 2, when we are talking about this one value to be positive, and there can be two cuts, two zeros of this function fx, which we have written in rho to be 0. In that case, when it have two real values, it should have three real values solutions. So we must ensure that that solution is on the left side, right? But we haven't ensured.
I think it was like this in the x space. Yeah. So in this space it will be like this. I mean in rho space it will be like this. Okay. In the x space, if I remember, here it was 1 over 2 gm, right?
Yeah.
So the function was like this.
Yeah.
So like this.
No, not this one. For the positive one, right?
Positive one.
Okay.
For
For positive, it will go. There will be.
Yeah, there has to be. If it's positive,
yes,
then
they have to
at
be
negative value there has to be a 0, right?
Yeah,
So it's
but
positive here, negative at minus infinity.
So it has to be.
So there has to be a 0 somewhere between minus infinity and 0.
Yes.
See, if the function is positive here on the x equal to 0 axis, right? There has to be a 0 between x equal to 0 and x equal to minus infinity.
That x equals to minus
Okay,
infinity.
we just didn't draw that part,
yes.
but
Yeah,
it's clear there has to be a 0 there.
That in case of this negative part, there can be two complex in case of.
Yeah, that can be too complex.
There can be two
Yeah.
complex.
Because that's the case where you drew the card like this, right? Versus x, when you're plotting in the x, there is one possibility like this.
Yes.
Right? So one real but other two are complex.
In that case. Even if they are real and on the left hand side of the problem, that is not our region of
Yeah,
interest.
but even if it become like this, it doesn't make a difference for our purpose. Right? Because the physical region is only here. Okay, any other question? Okay, so then let's ask what happens at rho equal to 2gr. So it turns out that the singularity or apparent singularity of the metric at rho equal to 2 gm is a coordinate singularity. It can be changed by using coordinate transformation. Now, if you didn't know about coordinate transformation, right, and if you had to check if it's singular or not, okay, what you could do is to calculate the Riemann tensor and try to take various combinations and see if any of them become singular. Because if any scalar combination of Riemann tensor becomes singular, right, so the reach is scalar, or R mu nu rho sigma, R mu nu rho sigma contracted, right. If any of them become infinite, then you know that this cannot be removed by the coordinate transformation, because that is a scalar, right. The scalar things don't change under coordinate transformation.
Isn't that true that if there is a independent manifold singularity rather than coordinate singularity, R mu nu kappa lambda itself has a singularity, some degrees of freedom of
R mu nu kappa lambda having singularity doesn't mean that the manifold has singularity. If you look at R mu nu kappa lambda in a singular coordinate system, it will have singularity. Right? But it's a tensor, right?
Yeah. So I need always scalars to understand about the singularity.
Yeah. So if you want to use the curvature Riemann tensor to check if the manifold is singular or not, you have to look at scalars. Okay. But there are examples of singular manifolds where none of the Riemann tensor, the scalars that you construct are singular. Nevertheless, the manifold is singular, right? In the sense that there is no coordinate transformation that can remove the singularity. But we will not discuss them at least not now.
Sir,
Yes.
in this case, what we interpret by singularity is that the metric component going to 0 or 1 by 0 kind of thing.
Both, in the sense that if the metric component going to 0 by itself is not a problem. If the inverse metric becomes singular, that's a problem.
Like GRR goes as 1 by 0.
But see, that doesn't, yeah, GRR in this case goes as 1 over 0, so that's certainly a problem. Okay. But even if GRR didn't go as 1 over 0, okay, suppose only G00 went to 0, the inverse, G upper mu nu, we have 1 over 0 there, right? So that's again singular. So the singularity means either some component of G mu nu or some component of inverse of G mu nu is infinite. Okay. That's a clear signature of singularity. Okay. There can of course be more subtle singularities where not G mu nu but some derivative of it becomes 0, becomes infinite. Okay. Because take for example G which goes as square root of x minus x naught. Okay. Then G is perfectly fine, but the derivative of G will have divergence, right? Because after that 1 over square root of x minus x naught. Okay. So that could give rise to singularity in the Riemann tensor. Okay, so let's see what happens at G equal to rho equal to 2 gm. So let me write down the metric again. So I'll demonstrate that there is no singularity by going to an manifested non-singular coordinate system. And then the angular part which I'll write as rho square d omega square. Okay, this is just to avoid writing this combination every time. So d omega square will basically stand for this combination. Define first the new radial coordinate rho star, which is rho plus 2 gm log rho 2 gm plus 1. Okay, this coordinate transformation of course is singular at rho equal to 2 gm. But we expect that if you have to remove a singularity, an apparently singular metric, if you want to make it non-singular, right, the coordinate transformation at least has to be singular. So okay, we make this singular coordinate transformation. But this is not a coordinate we are going to use. We define V as P plus rho star. And then we will use V d theta phi, sorry, V rho theta phi as coordinates. So these coordinates, these are known as ingoing Eddington-Finkelstein coordinate. Okay, there is also an outgoing Eddington-Finkelstein coordinate where you just change the sign of this to minus. Okay, but these are more useful.
What is the name of it?
Eddington-Finkelstein coordinate, and it's ingoing. Okay, we'll see why it's ingoing. Okay. But I'm saying there is also a version of this coordinate system where you change this sign to minus. That is called the outgoing Eddington-Finkelstein coordinate.
We just change the row, like just take one change, like we don't use V.
If we just change row to row star,
Yes.
that will not help. That will not make the thing non-singular.
So we are using V and row instead of V and row star.
Yes, yes. We are using V and row. Okay?
So only the time component has changed.
Exactly. Only the time component, so radial component I have kept as row. Okay. The time component I have just added some function of row to the time component. Right? Because the row star is just a function of row. Is this okay? Now this coordinate change is sufficiently simple, okay, and it's a simple exercise to check or calculate the new metric. So exercise is to check that ds square in this coordinate system is minus 1 minus 2gm by rho dv square plus 2 dv rho plus rho square dv square. Okay, what you can do is you can start from this. Calculate dv. dv is just dt plus d rho star, and d rho star you can easily calculate in terms of d rho from here. Substitute there, and you will find this metric.
So this short term solution is valid up to the physical radius or up to the short term?
Formally it's valid everywhere. Even for rho less than 2gm, this solves Einstein's equation.
That will change the signature.
No, you cannot say because this becomes plus, this becomes minus.
The whole thing.
So the signature remains the same, right? Because the signature counts how many positive and how many negative eigenvalues we have, right? So if rho is less than 2gm, it's perfectly valid solution because this changes from minus to plus, but this changes from plus to minus.
Sir, if we cannot discuss with this metric, the
Yes.
initial metric about when rho is equal to 2gm, right?
Yes,
But we can discuss about it when it is inside, right?
yes, we can.
So in that case, what we can see that the eigenvalue corresponding to the space part changes sign.
But that is not the space part. That's the point. I mean, you shouldn't call it space part, right?
Yeah.
But what tells you what is space, what is time?
Yeah, what I'm trying to ask that we can see it in this fashion that the nature of this space coordinate or this row coordinate start behaving like a time coordinate. And
But that makes sense only if you can first argue that rho equal to 2gm is non-singular, right? Otherwise, you can never go from inside to outside to inside.
okay. In that case, what remains inside remains inside.
Exactly. I mean, there's no the two solutions are completely disconnected. You can get one solution inside with this property, then you will call rho as t, right? It will be
Yes,
a time
absolutely.
dependent solution.
Yes.
But that will not be connected to anything outside if the surface rho equal to 2gm was singular. Right? So to discuss the inside, right? Because we are thinking of it from the perspective of the outside observer, right? That we are sitting outside, these are steps of the metric of a massive particle, massive object, right? Massive particle. So from our perspective, if you want to discuss the inside, right, we first have to make sure that rho equal to 2gm is not a singular surface. That only then we can hope to talk about inside. Okay, otherwise it's just a completely independent solution of the Einstein's equation. Okay, so now you see that this component still vanishes, right? At rho equal to 2gm, this is still 0. But the metric you can check is non-singular. Why? Because first of all it becomes 0. Okay, that's okay. I mean metric component becoming 0 is not a problem. We have to make sure that G inverse exists. So let's look at the structure of G
Have to find out
at rho equal to 2gm. The metric G mu nu has the following structure. See, there is no dv square component. Okay? So we write v rho theta phi. Okay? V rho theta phi. So 0, 1, 0, 0, dv d rho, right? That coefficient is 2. I assign 1 to g0 and 1 to g rho v. Okay, because this is g mu dx rho dx, right? So that contains g rho v dv d rho and g 0 dv d rho. G rho v and g 0 are the same, right? They are the symmetry. So 1, 1. These are all 0. And then you have rho square and rho square sine square theta.
This is not 0. Determinant
This
is not 0.
is perfectly invertible. It's a diagonal matrix. These of course has an inverse. This also has an inverse. Right? Its inverse is itself 0, 1, 1, 0. So neither G mu nor G inverse is singular.
Sir,
Yes.
if your component is any component of the metric goes to 0,
Yes.
and here you are safe because you have a cross term which is even after changing dv you have a dx square,
Exactly.
right? So if any component goes to 0 and you won't have any such cross term, then it will automatically.
Exactly. That means that if there is one row and one column vanishes completely,
Yeah.
then you have problem, right? And that kind of matrix is not invertible.
Yeah.
So that their matrix certainly has singularity. It could be coordinate singularity, it could be something else, but clearly it's a
Can I
singularity.
define my singularity as a point at which if I change my any coordinate, any one of the coordinate, and still I am not able to change the point in my whole metric space?
The point in your whole matrix is
Because ds square will be 0, so the point will be the same. Like that.
well, the point is there kind of metric which blows up, right? Or the
Yeah, again then if it's within a d small change of my coordinates, I am getting a huge change in
but
my-
that could be coordinate singularity.
Yeah.
Right? So to ask if there is a genuine singularity, you have to check other things.
Yeah.
Right? A coordinate singularity is one, yes, if you change it, that way, then if there are some directions in which you change the coordinate and the distance is 0, right? Which basically means that the matrix has a 0 eigenvector, 0 eigenvalue. Right? Then it's singular. Right? But having a 0 eigenvector means it doesn't have an inverse. Right? So it's the same sense. Other G or G inverse has to blow up. As I said, there can be more complicated singularities where neither G nor G. Well, when G has some square root singularities, for example, right? Okay, G inverse can also be perfectly fine,
But the derivatives can.
but the derivatives will blow up, right? But let's not worry about those singularities right now. Here clearly it's non-singular. This shows, right, that there is not even any derivative which is blowing up. So in this coordinate system, it's clear that the metric R, the R rho equal to 2gm is not singular surface. Right? Where you can make a simple change of coordinates to remove that singularity.
In our theory, we are talking about C2 manifolds, like up to second order derivative, like manifolds differentiable up to second order.
No, there can hard derivatives which can become singular. That's also could be a problem. Because
Like
d
in
mu
our-
nu or mu nu rho sigma, right? That also you don't want to be singular, right?
Yes. So in case of, like in our theory, we are always talking about C infinity functions.
No, you don't have to. You can allow for non-C infinity functions, right? But you have to interpret what the singularities mean. Right? So that, I mean, what is allowed and what is not allowed, that you have to decide afterwards. But whether it's singular or not, that you can see, right? That if the certain derivative of the Riemann tensor becomes singular, okay, and if you can remove it by coordinate transformation, then you will call the matrix singular. It's still maybe acceptable, right? If your action,
That is
for example,
similar-
doesn't contain high derivative terms of that kind.
The case we are talking about, that in case of higher derivatives of G mu nu having a singularity, means that in those cases my functions we are talking about are not differentiable up to a high order.
Yeah.
In that case, my manifold itself contains a problem Is that always true? For
No, it's whether it contains problem or not, as I said, that depends on the physical situation. Sometimes you may allow such
Yes.
singularities, right? So whether it's actually problematic or not, that's something that you have to decide.
But at least of the first order, we can say the determinant of g actually determines that the function is differentiable. The function is my g, like the coordinate system is, or rather the manifold is singular at that point.
No, determinant of g is perfectly fine here. The determinant of g by itself is not enough.
No, what I'm trying to say that here we can.
That is the eigenvalue, but determinant of g can be perfectly finite.
But sir, if one of the eigenvalue is itself 0,
The other one is blowing up. Right? This Schwarzschild metric has determinant of g, there is no singularity in determinant g, even in the original row coordinate system, right? Row t coordinate system. Okay. The question is whether the some of the eigenvalues are blowing up or not. Right? If some of the eigenvalues are blowing up or becoming 0, then we have a problem. Then at least we have a coordinate singularity.
But here the one eigenvalue is blowing up, another is not
Going to 0.
it's
The other is
going
going
to
to 0. Yeah.
So the multiple actually considered.
Exactly. Okay, are there any other questions? Okay, so this demonstrates that this rho equal to 2gm surface is non-singular. But what you want to do now is to study this non-singular coordinate system to see what's going on near rho equal to 2gm. So let me draw this rho D space. So rho equal to 0 turns out to be a genuine singularity, so we don't want to go beyond rho equal to 0. But this is my rho equal to 2gm. Okay, where nothing really goes on in this mix, nothing becomes singular. Now we want to know.
Sir,
Yes.
rho equal to 0 is a essential singularity. How can see it from here? Because in that case also, when we are using this not this v coordinate but the t coordinate,
Yes.
in that case this rho equal to 0 gives me infinity in one place and a 0 in the other place. Right?
Yes. So rho equal to 0, to see that it's singular, you cannot see it from here, no?
Yeah, we
So
have
because
to
you have to calculate the Riemann tensor to check its
One of the scalars,
scalar
some of the
invariant
scalar-
and then check that something goes up.
So that is something
In the
inherent.
inverse, we see that will blow up. Even if we do this coordinate, the inverse will blow up at 2.
But there may be other coordinates.
Yeah,
There may be other
coordinate
system where it is not.
where it doesn't blow up. Right?
So very
I mean, just by examining a metric, it's hard to see that in a given coordinate system whether it's singular or not.
So like the solution itself predicts the singularity of the given manifold at rho equal to 0, right?
This solution is singular. That's the
Yeah,
same.
the solution is
You
singular
have to
at rho
calculate
equal to
aluminium rho sigma and check that it's singular. That is a scalar quantity which diverges.
then it is essential singularity.
Yeah, then that means it's not a coordinate singularity, right? This is genuine singularity of the metric that you cannot remove by coordinate transformation.
And something that is invariant by coordinate transformation is that diverges, that means
It's singular, exactly. That's right. Okay. So now we want to see how a motion of a particle in this space time will look like. Okay, and we will be using this coordinate system. Now to determine the motion of a particle, one useful notion is what is called the light pole, okay, which limits the region, the possible curves along which a particle can travel. Okay. Not necessarily geodesics, okay, but any possible curve that a physical particle can travel in. Okay, in a space-time diagram, okay, not every curve is a possible particle trajectory. Okay. And that follows from the requirement that ds square cannot be positive for a physical particle. Okay. ds square is minus d tau square. For light, it can be 0. Okay. For physical particles, ds square has to be negative because d tau square has to be positive. Right? For massive particles, ds square has to be negative. So we try to impose that condition, ds square less than 0. So this says, so this of course is strictly positive. Okay. So if ds square is less than 0, we can demand that this is less than 0. Right? That's certainly a necessary condition. Okay? Because if this is not less than 0, then you cannot have the whole thing less than 0. Okay? So you just focus on this. Okay? So this is the extreme case where d omega is 0. Okay? There is no motion in theta and phi direction. So these are called radial direction, radial motion. Okay? That's the extreme case. Okay? Motion in theta phi direction is not going to affect this. So ds square less than 0 tells us that 1 minus 2 gm by rho times dv d rho square plus 2 dv d rho minus 2 dv d rho must be positive or 0. 0 is for light. Okay. So this I can write as dv d rho times 1 minus 2 gm over rho dv d rho minus 2 let it be equal to 0. Is this okay? So first, let's draw the boundaries. Okay, then you will see which is allowed region. So boundaries are when dv d rho is 0, the other boundary is when this is 0. Okay? Because that's the place where this actually the inequality becomes equality. So dv d rho boundary, dv d rho equal to 0 boundary is clear. It's horizontal axis. This boundary is when dv d rho is 2 over 1 minus 2 gm over rho. dv d rho is some positive number. Is clear? Right? Because yeah, as long as rho is larger than 2 gm, okay, that's how you are drawing it now. Okay. This is positive, so dv d rho is 2 over something. Okay, it's positive, but it's larger than or more larger than 45 degrees. So it's some line like this, more than 45 degrees. Okay, I am just drawing at any given point. Okay, for a fixed value of rho. Okay, this has been done for fixed rho. I'll later on discuss how it changes as a function of rho.
Rho equal to 2 gm is a special point.
So rho equal to 2 gm we are now not considering, so we are still taking rho greater than 2 gm. We have to see what happens at rho equal to 2 gm.
These are the solution that it is equal when it's equal to 0.
Very equal, right? Now we want to know what is the allowed regions. Right? So what does it mean? This means that these two lines divide the allowed regions from the disallowed region, right? Because these are the places where this actually vanishes, right? Now on one side of it will become negative, on the other side it becomes positive, and you want to determine which side is what. That actually is not hard to see, because you see if dv d rho is positive, then this dv d rho this also must be positive. Right? Which means that dv d rho has some kind of lower bound. Is that clear? If dv d rho is positive, then the second one says that dv d rho has a lower bound. Okay? Which means that it must be this region. This is the allowed region. Why? Because suppose you are here. Suppose you are here. Okay? dv d rho is still positive. Right? Because we are still, let me draw the slide quickly. Take a line like this. Okay? So for this line, this line, dV0 is still positive, right? Okay, it's sloping this way. Now we know that there is a lower bound on dV0, not an upper bound from this. Right? Because if dV0 is positive, then this dV0 also has to be greater than something. Okay. Which means that if it was on this side, this would be acting as an upper bound. Right? If it is on this side, then this line acts as a lower bound. Right? So which means that this must be the region which is the allowed region. Is that point clear? Right? Just draw a line like this. Okay, which is still has positive slope, but it has a property that it's on the left of this line. This satisfies the relation that dV0 is positive as well as dV0 is larger than this bound. Okay, and that should be in the allowed region, because dV0 is positive, then dV0 should also have be beyond some fixed number, okay, above the lower bound. This region is negative. Why? Suppose I have a line like this. For this line, dV0 is positive, but it's less than the boundary. Right? So dV0 is positive, but this dV0 is less than 2 over this. So that means that this quantity will now be negative, right? Which is outside this range.
Can we see it from 0 part? From this dV0?
Yes, you can also see it from there in near this region.
If you just make it a little bit negative,
Yes.
that will not make the right hand side to be positive. Negative.
See, this is negative, right?
Yeah, so that is not negative, because we know that for dV0 a specific value is equal to 2. dV0 by 1 minus 2 rho g is equal to, when dV0 equal to 2 by 1 minus 2 gm by rho, then the right hand side becomes 0.
Yes.
So if dV0 is small negative number, that cannot make the whole thing
Yeah,
negative.
so suppose dV0 is this. That's what you want to know.
Small negative number, small negative.
So it's here. Here. Yes.
Here or lower side actually.
Yeah. So that corresponds to here.
Yes.
We have to go lower. It's the same argument. No, I mean, this is the same line which is extending to the other side.
Yes.
Right? So if you change the sign of everything, this is the same dV0.
Actually, what I'm trying to think that maybe 0 will be easier to think actually,
No,
because
this is easy enough, right? Yeah, you can think it in many different ways. Right?
Yes.
You'll always get the same result.
Mhm.
Right? Is that you have two lines, right? And you know that of that some region bounded by these two lines is an allowed region. The other regions are not. Okay, I gave you one argument to say that this is allowed. If this is allowed, then of course this is also allowed. Right? Because it's the same lines passed through these two regions, right? The slope doesn't change. So this is an allowed line. Okay? And this is also an allowed line. Okay, that we can conclude because there is no boundary between these. Okay, I'm not crossing this, it doesn't vanish, right? So that means if this was positive for this line, it will remain positive for this line. These regions are disallowed, which means no particle can travel along these trajectories. Is this clear? So in this region, this product will be negative. Okay, again I am working with this positive.
Sir, in this, between these two regions,
Yes.
sir, there also this term carbon negative.
In this region, here.
Sir, here this is small region.
Which
Sir.
region? This region?
No, sir, this, sir, in first coordinate, the
Let me-
underline line.
Yeah. So this is the line in the first quadrant here. You want to
Sir, not here, sir, I think is small region. Sir,
In this
in this
region?
figure is small
The
region.
dash, I think the dash portion and the allowed that is in between.
the other unallowed region.
Sir, in first coordinate, undashed portion.
here.
Undashed
quadrant,
portion.
Allowed and
Just
dash
better than
line.
this slanted line, just better than
quadrant.
the allowed.
That is allowed.
In allowed region.
Yes, so this whole region is allowed. That's what if this region is allowed, right? Let me forget about all this. What I mean, if this is the allowed region, so is this. Because the line, see, the constant is on dv0, no? So if a line passes like this, then it's the same dv0. It's the same straight line after all.
Oh, sorry.
Right? If line passes like this, so if this is allowed, its diametric, its opposite part is also allowed, right? Because it's just passing like this. Is that okay? Right, so you can easily check that the point here. So this slope, this is the line around which dv0 is 2 over 1 minus 2 gm over rho. So if you draw any line like this, then you can easily verify that this product that you will get will remain positive. Is this okay? You are still have some confusion? Okay, if it's not completely clear, you can just verify explicitly, right? Just take some point, take some value of this ratio, right? And then plot and see, make sure that this satisfies the correct constraint. Okay, now, so this tells us that the possible particle trajectories, okay, that starts from a given point here, okay, must have its tangent lying in one of these directions. Right? That you cannot have a particle. So suppose starting from here, you say the tangent to the curve is along this direction. That's not possible. Right? Any tangent, okay, any direction locally here, it has to be directed in this region, okay, or in this region. But of course, this angle will keep changing as you move from one point to another point, right? Because it depends on rho. So, what angle at a given point, right? Which angle it can go into will change as you change rho. Okay, we'll worry about that in a few minutes. But there is one more important thing you have to determine, which again is obvious in Minkowski space, but not always in all space time. Is the notion of future. In Minkowski space, let's look at the Minkowski space t versus x. Suppose this is t, this is x. Any line in this region is in the line code, right? dt square is larger than dr square, dx square. Right? These lines are not allowed trajectories. But there you also have a notion of future, right? Which direction is the future of the particle. Okay? For example, if you say that a particle moves like this, this line, okay, does satisfy the constraint that ds square is less than 0. But this is not an allowed trajectory, right? Because we know that a time always increases along the trajectory. As the proper time of the particle increases, the coordinate t increases. That's a convention. Right? You could have declared minus t as your time coordinate, right? In which case, t will always decrease as proper time increases. Okay, but we choose one convention that t increases as proper time increases, so that fixes the notion of future. Okay, which direction is future? So when you draw a trajectory like this, you have to also draw an arrow as to which direction is future. Is this clear? Now suppose somebody has given you an arbitrary metric, right, where even the time coordinate is not very visible, right? It's not even clear which one is time coordinate, right? Or for example, the metric that I wrote in terms of v and rho, right? It was not clear in which one you should interpret as time coordinate, right? Because the metric has off-diagonal components and so on. Given a metric like that, how do we determine which is the future direction? Okay, so you have drawn the light cone, okay, that allowed trajectories in this region, but will the particle, a physical particle, go this way or this way?
We can explicitly check it.
Yeah, so what exactly you mean by explicitly check it? Right?
Taking a particle.
So if I go to a local inertia from there, if I
Go to a frame in which you are
But t goes to minus t is always keeps the metric unchanged, right? So by going to a local inertial frame, you will not know which is the correct tau t of the particle. Okay. So if somebody gives you the metric and nothing else, you know the light codes, okay, you know what are the allowed particle trajectories, but you have no way of drawing an arrow, okay, because you have not declared what is your time coordinate, right? What is the, I mean, you could equally well draw your arrow in the opposite direction, right? Even the Minkowski metric, right? We know that dt square has to be larger than dx square, because otherwise ds square will become negative, or d tau square will become negative. So that much you know, okay? But along the physical trajectory, okay, as in the future of the particle, when d tau increases, whether t increases or decreases, there is nothing which can tell you. If somebody just gave you the Minkowski metric and nothing else, right? Both are allowed, right? dt d tau could be either positive or negative.
So that proves that we is by our convention we draw.
Exactly. So by our convention we draw, we say that t increases with tau. Okay, that's because there is a notion of t. Right? In a general metric like this,
also do that.
yes.
In local inertial frame, I can also define my t's in such a way. For this
Yes, but the relation between local inertial coordinates and these coordinates, right, is not unique, because you can always take t to minus t,
okay.
right, and it will still satisfy the eta mu equal to minus 1 1 1 1 condition, right? So yes, you are right. If in a local inertial frame you have notion of which is future, right, and if you knew the coordinate transformation between local inertial frame and this thing, then you could do that, right? But in the local inertial frame, you can always take t to minus t, right, and declare that minus t as your t. Right? So that by itself will not tell you what the future is. So the only way you can decide unambiguously what the future is.
So here we have started with this t-rho coordinate system.
Yes.
In that coordinate system, we have taken t to be time and taken
But
t to be
who tells you that t is time? So the point is that the only reason that you can fix the notion of time is because there is an asymptotic geometry where we have normal Minkowski space. Okay. So there you choose your convention, you declare something as your time. Then you could declare t as your time, you can declare minus t as your time. Okay. But that's the place where you have some notion of what is future. Okay. So the idea is that you fix your time there, okay, asymptotic region, okay, which is large r. Okay. There you know that increasing t should be the correct direction of arrow. Okay. So that fixes, okay, in which direction the arrow should be, okay, inside the light cone in one region of space, okay, asymptotic region. Then you basically continuously move the light cone. Light cones move continuously, right? Okay. And as it moves continuously, these two regions are always disconnected, right? So if you know, for example, far away, okay, this after all, let's look at what happens as rho goes to infinity. That's the asymptotic region, right? As rho goes to infinity, okay, this goes to 0. So it basically will, this slope will go to 1, right? This slope dv0 will become 2. Okay, so this has slope 2, this has slope 0, and here you can try to decide what is the notion of time, what is the notion of future.
That we can same do with the coordinate system we started with, right?
Yeah, so that you could do with the coordinate system we started with, because the t-rho coordinate system was designed so that asymptotically it looks like flat Minkowski space.
Yes. And in that
This one, even asymptotically it doesn't look like flat Minkowski space, right? I have erased the metric, but if you look at the metric, right, it had a dv0 cross. That certainly doesn't look like Minkowski space, even for rho goes to infinity region. So what you do is that you go to rho equal to infinity region, then use the fact, okay, again it's a convention, okay, but you use a convention that as increasing t in that region, increasing t is a future.
So this is the one convention you have followed. One can do the same thing at any given point.
But at any given point, we don't know what is the notion of future.
No, but what I am saying is, I will give you a particular coordinate transformation.
Yes.
To go to a flat metric in that point.
Yes.
And use that, and in that flat metric only you will have a positive t as a future.
Yes, you can do that,
This is
but
what
that
I-
may not agree
Huh.
with your notion of positive t in asymptotic time, right?
Yeah, it won't agree with that.
Right? So in that case, to interpret this solution as an asymptotic solution and interpret the light cone direction, the future notion of future, to match with your notion of future in asymptotic region,
Okay.
it will not
That
work.
is more justified.
Yeah, so the point is you already know asymptotically, right? What coordinate that is the notion. So asymptotically you know which is the future directed arrow. Okay? And then you simply continue it slowly as the light cone keeps changing. Is that clear? Okay. So asymptotically, large low. There, T going up is the future, right? Now, I have raised the relation between the T and V.
But T only comes in the relation of V.
Yeah.
This T.
So V is T plus rho star. V is T plus rho star, and rho star is a function of rho, right? It's a function of rho. So if we keep rho fixed and increase T, then in the V rho coordinate system that corresponds to keeping rho fixed and increasing V. Right? So a vertically upward line should be future directed. Okay? If the line goes vertically up, that should be counted as future because that's the notion that matches with the asymptotic observer's notion. So this is future. This is future.
So you're saying for a fixed rho, increasing T implies increasing V. So future
Exactly.
T is future in V also. Right?
Yes, asymptotically. It may not remain like that everywhere. Okay? In this case, it does, but there are coordinate systems, as you will see, the notion will change. Okay? But at least in this coordinate system, we know this is future, okay, asymptotically. Okay? Which basically means that we can now draw arrows like this. If I do it correctly, this is, yeah. Okay. So, particle, the allowed particle trajectories have to go like this. Right? I say that here, for example, the tangent must lie in this cone, right, in this angle. Okay? But now it also shows which direction the tangent should be. Right? As the particle moves, as the property of the particle goes up, the tangent should be directed this way and not this way. Is this clear?
Light, this and this direction is same.
Yeah. So light can move along this, okay, but with time it will go like this and like this.
Both.
Yeah, you can throw light. So one corresponds to in this language as radially outward, the other corresponds to radially inwards. Right? Because along this direction rho is increasing, along this direction rho is decreasing.
So there
Here
are
the time.
Pardon? Yes.
Here light is not taking your time.
Yeah, this is not the time, but as the affine parameter is increasing, right, you can still ask which direction it will be traveling, right? And it's this. So basically, the light cone means, so this means that any future directed motion will lie in this cone, okay, with the arrow going up. Well, going not to say going up, I mean it can go this way, but this fixes the direction of the arrow. Okay, you can just continuously deform and see which of the arrow will be. Okay, now let's look at the light cones. Okay, we'll now draw in this graph. And so when I draw the light cone, I'll also draw the arrows. Okay, because that will tell us in which direction it can go. So here, far away, the light cone will be like this. Okay, this has slope 2. This is slope 0. That's what we have determined, right? Particle goes on this way. Now, as you come closer here, this slope of course doesn't change, right? dv0 is equal to 0. That's always one of the directions. But this slope, what happens to this slope?
This will
will be lesser.
You look at this formula, dv0 is 2 over 1 minus 2 gm over rho, right?
Decreases.
As
Yes.
rho increases,
So dv0 will increase.
dv0 will increase, right? So the slope is going to increase, right? So this is going to tilt like this.
Sir, but
Yes.
this is it should be in rho star actually.
No.
Rho star.
rho star we
What
haven't
is
taken as a
different?
coordinate. We have taken rho to be a coordinate.
Yeah, I have taken rho, v and rho as coordinates, right? Rho star was used to define v, because rho, v was t plus rho star. So you see that it is tilted a little, right? If you go even far closer, it tilts even more. Now what happens when you are very close?
Perpendicular.
It becomes almost perpendicular. Okay? So now let's imagine that a particle is entering the event horizon, rho equal to 2 gm. Right? At rho is equal to 2 gm, the light cone is exactly 90 degree, right? It looks 90 degree in this diagram. Any future directed motion of this particle is in this direction. Okay, that means towards the direction of decreasing rho. If you go here, it's even worse, it's like this. Okay, you can calculate this, it becomes negative. dv0 becomes 2 over 1 minus 2 gm over rho. For rho less than 2 gm, it's negative, right? It's because the metric is non-singular in this coordinate system, we can continue past with rho equal to 2 gm, right? Nothing really goes wrong at rho equal to 2 gm. So it becomes like this. So again, we see that the particle must move towards decreasing rho. Which means that once you cross this line,
You cannot.
there is no way to come back. Okay? And for this, the notion of future is important, right? If, for example, a particle was allowed to travel in this direction, it could come out. Okay? So you have to fix the notion of future, which you did by going in the far past or far away from the system. Okay? With that notion, we see that the trajectory of a particle can never come out.
So you said that the direction of T that will fix the direction of V in asymptotic region.
Yes.
It may not be the case in
Yes, but it has to be continuous. The notion of future cannot suddenly jump. Okay. If the metric is smooth, right, then the notion of future should change continuously, right? And that's what we are using. So you fix the notion of future by going far away, and then we basically use the same notion of future by smoothly continuing that to this. Yes.
One question, in this equation of V equals to T plus rho star,
Yes.
keeping rho fixed, you have notion that as T increases, my V increases.
Yes, exactly.
But why this asymptotic limit had to be brought into picture? Like you have this value for any rho constant.
Yeah, that is true. But the notion of what is future is only valid asymptotically, because that's what you know. Right? In this case, it so happens that you could apply it anywhere. Right? But there are other instances, right, where the relation is not like V equal to T plus rho star. It's a more complicated relation between V and T and rho star. Right? In which case, increasing T may correspond to something else in some region. So, what is future, okay, has to be determined asymptotically by going to the asymptotic region. See, increasing T, for example, is, if you go to the Schwarzschild coordinate, right, the original rho T coordinate, okay, T becomes space-like, right, for rho less than 2 gm. In which case, increasing T, what fixes the T has to increase, right? That's not even a allowed trajectory, right? Keeping rho fixed and changing T. So, if you want to fix the notion of future, you shouldn't rely on a coordinate. You have to rely on the asymptotic region, right? Where you can match with the notion of space-time that we are familiar with, where we have a notion of time. You use that to fix your notion of future.
But asymptotically, trivially in every space time it would be increasing t would always imply the future, right? Because it would be always.
If you use the coordinate system t, yes, right. Now the point is that I have used this. If I make a very complicated change of coordinates, right, then it need not be that always increasing t corresponds to the future. Okay, in fact, we will see an example where increasing t will not correspond to future.
In the asymptotic limit also.
No, asymptotic limit increasing t corresponds to future.
Okay.
But in the interior, you cannot determine the direction of future by saying that t will increase. Yeah, that's the point, that t could start decreasing, okay, in the interior. But the notion of light cone should change continuously. That's the thing you can use. Okay. So the two ingredients are that asymptotically you know what is the notion of future. That's what you use to fix which is future direction, and then simply continue, okay, smoothly to any other region of space time to determine the notion of future.
So, sir, at rho is equal to 0, time will disappear. Like
At rho equal to 0 is a singular point, right?
light cone will.
There you cannot define anything because that's why the metric is singular. So you cannot ask, even using standard classical general relativity, you cannot ask what happens at rho equal to 0. Right? This question could only be asked if there is a coordinate transformation that removes the singularity. Because then you could go to that coordinate system and ask what's happening to the notion of time. Right?
So from diagram it appears that this those two lines which are making some angle, it will make angle 0 at rho is equal to 0.
Exactly, yes.
So that means no further time, no future.
No, so at rho equal to 0, yeah, you cannot ask anything beyond rho equal to 0. That's what the Riemann tensor.
So, but no need to ask.
Well, it depends on what you mean, no need to ask. I mean, if you fall through, right? You hit, suppose, I mean, somebody has actually taken a spaceship and fallen through the horizon of a black hole, right? And you reach rho equal to 0.
Yeah. So,
I mean, you have to ask what will happen to you, right? I mean, so in that case, I mean, from your perspective, maybe there is no need to ask. But if you are actually jumping into the black hole and hitting the rho equal to 0
but we
point.
know just before it what happened to it. So now we reached at that point. So.
But at that point, right, I mean, in my proper time, what's going to happen? This is a question you can ask, right? That person who is falling through, right, that person uses his or her proper time. Right? It doesn't matter what is rho, what is t. Right? I just take a spaceship and I jump in. Okay? And you can check that in my proper time, okay, finite proper time, I reach this point. And then the question is, what is going to happen to me? That question you cannot answer using classical general relativity. Right? Because at this point, things are singular.
So at that point, this equation is not valid.
At that point, nothing is valid. The classical general relativity equations cannot tell you what happens at that point, right? Because Riemann tensor becomes infinite. It's like if you have a point particle, right? Classical electromagnetism cannot really tell you what happens when you actually hit r equal to 0, right? Because electric field diverges. Right? We know, of course, the quantum mechanics repairs that problem. Okay, but just classical electrodynamics, you cannot ask this question, what happens exactly at the location of the point charge. Is this okay?
So a particle, if a particle crosses this horizon, this event horizon, it is certain that it is going to hit 0.
Yes, it's certain that it's going to hit 0 because the light cones are all directed towards decreasing rho.
Can I calculate that it is going to be in finite time?
Yes, you can calculate in the proper time of the particle, it is going to be at finite. That you can easily calculate. You just want to solve the geodesic equation. Right? Suppose you are just not using any engine, right? Then you just follow the geodesic equation and you can calculate how much proper time it will take. Right? Even if you are using an engine, right?
It will fall.
Powerful engine, you can prevent falling by driving it regularly in the opposite direction.
But massive.
Whatever happens, you cannot go out of the light cone here.
Inside.
Right? So eventually you will have to fall in.
So in a black hole, there cannot be any surface by definition. Inside the event horizon,
Yes.
there cannot be any massive surface. everything have to collapse to a single
Very massive surface. What is the
point.
meaning
Like
of
a solid surface. Like
Non-ready.
But yeah, everything has to. Yeah, I mean, it cannot be static.
Yeah.
It cannot be a static object. Static in the usual conventional
Yeah,
sense, right?
yeah.
That if you cannot sit at rho equal to rho star,
Yeah.
rho naught.
for example,
Because rho equal. Suppose you want to sit at rho equal to rho naught, right? That's like vertically going down.
yeah, that I cannot do.
That you cannot do because that's outside the light cone.
Yes, absolutely.
Right? So
And,
you cannot be static at rho equal to rho naught
yes.
at any fixed rho naught inside the element horizon. Outside you can, right? Because even if very close to this, right? The slope is almost 90 degree but not quite 90 degree, right?
So
if you have a very
very
powerful
particle-
engine, you could still avoid going inwards.
Yes. Like what I'm asking because like even in Newtonian gravity, if we try to define very small massive particle, then the escape velocity increases very rapidly. In that case, if we define
But escape velocity never becomes infinite. You can always escape however close to the center you go.
yeah, but if we like put that velocity of light is the maximum limit, then there
Yeah,
can
if
be
you
a
put the velocity of
possibility.
light to the maximum limit, right?
In that case, like
Yeah, but upon in that regime, of course, classical Newtonian gravity is not valid.
yes,
Sir, we got that light for light for a rho equal to 2gm. What is the implication of this vertical line for a light signal?
Yeah, so light signal, radial light signal, that goes up like this. So even light cannot come out.
This one is going inwards, right?
This one is going inward, this one is going outwards.
No, it is at rho equal to 2gm only, right?
Yes. So this one is like outgoing, radially outgoing. Like.
Really outgoing, but that at rho equal to 2gm for this.
So this light basically goes around the horizon.
It is circumventing.
Yes, exactly. Because it's if you take this light going around this exactly at the horizon, right? That means what? It's fixing it's fixed at rho equal to rho star, right? So it's basically going around the horizon. Is this okay? Right? So from any point outside the horizon, right? You can have two extreme cases of light signal. One is radially inward, that's this direction. One is radially outward, that's this direction in this diagram. That radially outward direction, okay, here becomes around the horizon. Okay, that once you have reached here, you cannot send signal even radially outward. Is this okay? Now this also gives another interesting event, phenomenon, and that is the following question. Let's suppose that we are sitting at infinity, okay, or at some rho equal to rho naught, far away, and we have thrown in something towards the horizon. Okay, we see it going towards the horizon. The question is, when will we see it actually enter the horizon? Okay, we have to prove that it's never, right? So you can simply ask this question, right? You throw in a particle and see when it will enter the horizon. Okay? So let me draw the diagram again.
Reach the horizon or enter the horizon?
Enter the horizon. Well, once it has entered the horizon, of course you can never see it. Okay? But you want to see when it has actually seen that it has reached the horizon. So this is the diagram again. Rho versus d. This is rho equal to 2g. We are sitting somewhere here at fixed rho. Some rho now. P plus rho star. Okay. So this will be P plus rho star naught. And for corresponding rho naught, we can calculate some rho star naught. That's what we'll call rho star naught. So our word line is this one. Is going like this. Right? We are sitting at fixed rho naught. Okay, we have to run some engine because if we cannot sit still because we have to overcome the pull of gravity. But it has a mild engine that's keeping us at rho naught. That is, you are not also falling into the system.
And not more than our GDC. This will be not more than our GDC.
Yeah, if you want to keep yourself fixed at rho naught, right, without changing theta and phi, you are moving around with your AC. Right? You know that you cannot, even in Newtonian gravity, if you want to sit still at a point, right, you better run a small engine to prevent you from falling in. But this, of course, can be made as small as you like by going to sufficiently far. So we throw in some particle. Okay, so from here, the particle goes like this, it within the light cone, and it some then just falls in. So it has to.
Free particle, this cannot. Will
Yes.
it be straight?
Why straight?
Yeah, yeah.
In the VT space, of course, it can be curved, right?
Yeah.
Actually, it's
Then so a particle falls in like this. Okay? We don't even have to assume if the particle has an engine or not, and doesn't have an engine. Okay, we just let it go. Okay, that's when this, we are not claiming that this is necessarily geodesic. Okay, it enters here, and you have to see this particle entering the horizon. Okay, but in order for us to see it, the light that is emitted from here has to reach us. Okay, so when the particle is very close here, its light cone is like this. So it can send us signal, okay, it's a light signal, which is the most powerful, which has the chance of overcoming everything. But the light signal, radially outward light signal will be represented by this along this direction. Okay. So that's almost particle. See, this grazes the horizon. Okay. But of course, once it has come sufficiently far away, then it bends. Okay, it bends because the light cone itself, you know, is changing. Right, as you go a little far away from the horizon, it bends. So it bends, and eventually it will reach us. Here, well, the slope is not quite correct because it has to be larger than 2, but anyway, will eventually meet it somewhere. But it's clear that as it goes closer and closer to the horizon, it starts becoming more and more particle. And hence, it takes more and more time to reach us. Right? When it's exactly at the horizon, it will never reach us. Right? Because it's grazing the horizon, right? Then light can never escape, right? It's just grazing the horizon. So this says that in order for us to see the particle actually entering the horizon, okay, or reaching the horizon, it will take infinite time. Is this point clear?
Yes.
Because when the particle is at the horizon, we clearly know the light never is going to reach us. So it just goes straight on. When it is little beyond, okay, then yes, it can send signal, okay, and it can reach us, but that will take very, very large time. Okay, so the time that it takes goes to infinity as the particle goes closer and closer to the horizon. Okay, so in this sense, we will never really see anything falling into the black hole sitting at infinity.
So, like, if a person sits at a point,
Yes.
in some fixed row, in principle, like, in his lifetime, he is never going to see a particle reaching exactly to the horizon.
That's it, yes.
Because all the particles which are falling to the horizon, the light is coming so late.
Yeah, exactly. Okay, so that's what this is saying. This diagram is basically showing that. That
So even if we take rho naught very near to that, that will be parallel, no? So that as that
if you take rho naught to be here,
yeah, very
yes,
close.
yes.
Then also we will be seeing the distance in infinite.
Well, even exactly, because suppose you are at a fixed rho naught, right?
Yeah.
Okay. As the particle, as the thing approaches closer and closer to the horizon, right? It will still take infinity.
Yeah.
Yes.
So any finite rho naught, if you consider any finite rho naught, okay, then it will take infinite time for you to see anything that is actually entering the
Yeah,
horizon.
but accordingly, then this has to be very close to that. This will depend on the yeah.
Yeah, the observer you think of as you can be very close, but it's a fixed distance. You don't want to be yourself on the horizon, right? Because then you will never come back. So as long as you want to collect the data and come back, right, you have to be at least gently away from the horizon.
From very near also, we will not be able to see what happens to that.
Exactly. Even you are from very near, right? As long as you are a
Yeah.
small but finite distance away from the horizon, you will never be able to see that particle entering the horizon. Because in this sense, you cannot say that you may be sitting here, right? And you cannot say that I'll send another engine behind the particle, which will observe it entering the horizon and come back. Right? That's also not possible.
Yes.
Okay?
Sir,
Yes.
if two particles are like two objects are thrown like at the same instant, would
Yes.
they be in knowledge of each other like at that point key? Like there won't be any communication between them also in the at the horizon.
That is true, yes. I mean, if one is
Because like one's future cone is towards in one direction and the light cannot come back from that object to the other object.
yes, except that what can happen is that if one object, suppose the one behind, okay, has a big engine, okay, then that person can overcome and intercept the light on the other side. That imagine that you are here, right? The particle has entered. One of the particles is going like this. Okay. Now another particle falls a little behind. Okay. Light cone is still like this. But what can happen is that this one may run an engine that is going around this light cone as slow down as much as possible. This one may run an engine which is pushing it as much as possible towards rho equal to 0. Then eventually it could happen that they will intersect each other. This in fact will become clearer when we use another coordinate system. Okay, this what is called crucial coordinates. But in principle they could go and meet inside the horizon. Okay, neither of them will be able to send back any signal outside.
But they can.
Yes, but they could in principle be.
Could be provided they are related in beats or one is
But that is.
means one enters earlier and other enters later. Like,
Yes, that one enters earlier, other one enters later. Then the one which enters later could in principle
meet the earlier.
intercept the signal from the earlier one. Okay, that is in principle possible.
So sir, if you have actually a black hole and many particles and all have already fallen into it,
Yes.
so whenever you observe it, you will see those particles outside lying there, right?
Yes, that's right. If you classically, you will see all those particles lying. Exactly. You will never see anything ever entering the horizon.
So
Yeah,
you
so-
see all particles outside the black holes.
So people-
Except that there is another effect which you have also studied earlier. That is a red shift.
Yeah.
Right? At the horizon, G naught not goes to 0.
Yeah.
Right? So if you use that to calculate a red shift, right, then any light that this particle emits will be infinitely red shifted. Okay, so which means its wavelength will become infinitely large.
That light will never reach to us.
It will never reach to us, but
Even the
one is-
closest one will have a
even the
very
closest
large
one, as it goes
wavelength,
closer,
it
right?
cannot be detected.
as it goes closer but has not reached the horizon, okay, it sends some signal. Okay. That signal will come to us with very large red shift. Right? So before we even worry about whether the particle has entered or not, right, we'll not be able to even decode the signal that we are receiving, right? Because the wavelength of the light becomes larger and larger as the particle goes closer and closer to the horizon.
Okay, so for us, we have a limited wavelength to see, so we will see that it will go after that.
Yes, exactly. Yeah, after that we cannot even detect the particle very much. After we cannot really see what's going on to the particle. Okay. So from our point of view, we will see that as the particle is entering the horizon, it's slowing down infinitely, right? And its clock is also becoming slower and slower. Okay, because from the particle's viewpoint, of course, the clock is running at the usual speed.
But for our viewpoint, we will see the particle is not accelerating, rather deaccelerating.
Yeah, that's it.
Yeah, we will basically see the particle exactly. That the particle, the motion of the particle is slowing down, right? Infinitely. Okay? And not only the motion of the particle, but anything that all the clocks that the particle is carrying also is slowing down infinitely as
It will become redder and redder.
exactly. It will become redder and redder.
So the clock is slowing down, that part is slowing down. Why will we see that motion is
Because of the.
Because to see that it has entered the horizon, it takes infinite time, right?
Oh, so These defines will take infinite.
Exactly, right? To actually see, so going from here to here, right?
Takes many.
This will reach us sometime. This will reach us much longer, much later, right? And as it goes closer, it reaches us even much later, right? So in that sense, you will see this slowing down. Okay, but again, let me emphasize that if we actually see in terms of the proper time of the particle, right? If we draw a geodesy, suppose the particle has no engine, it's just falling through.
Okay.
You can calculate easily. Here you have write down a geodesic equation, right? You can take a radial geodesy. Okay, forget about theta and phi coordinate. You can write down a geodesic equation. You can solve for how much time it will take for the particle to form, say, fall from starting at rho equal to rho naught, some fixed value, to the horizon. Okay, to rho naught equal to 2 gm, to rho equal to 2 gm, and that you can calculate as a finite proper time. Okay, so if you are actually falling into the horizon, you will reach the horizon in a finite proper time.
In other words, this is happening due to the infinite redshift.
Yeah, meaning the point is the reason that we are not seeing it in finite time is because of the infinite redshift, but the particle will be falling through in finite proper time. Okay, so maybe I'll stop here. Tomorrow I'll introduce another coordinate system, okay, which makes some of the things easier to visualize. Okay, but the coordinate transformation itself is a little more complicated. So I'll do that tomorrow.